Okay. Hi everyone. So welcome back to part 3 of the first lecture on introduction of machine learning. So in this part, I'll actually go over some examples of machine learning in real world applications, right? All right. So before getting into the applications, I'll just kind of set some notation and just kind of recall again supervised learning from what we discussed last time, and also kind of set the premise over here, right? So we'll start with supervised learning, right? So supervised learning is essentially, if you recall, right, it's essentially the access where we have basically all the data labeled, right? So I'm assuming right now that we have all the data labeled. So I have essentially M training data points, right? And all the data points are labeled, right? So this is key in the supervised learning scenario. Of course, all of these can be extended to semi-supervised learning and active learning and all of these concepts. We'll actually kind of look at these much later in this course. Right now, we'll start with actually supervised learning. So we'll start with supervised learning and we'll study basically regression and classification for the most part, right? So the goal of supervised learning is where I have here the XM being the mth data point and YM being the mth label, right? So these are called features as we discussed last time, and these are called labels, right? And the goal of supervised learning over here is to find a function f such that f of xm, right? F of xm is actually a good approximation to ym, right? So ym is my label. So f of xm, I apply my f on my features and I get a good approximation of my label. And this should be a good approximation everywhere, right? That's the goal. So the goal again, just to kind of be more clear, is to actually predict the labels on unseen x values. So I think this is kind of very critical, which we'll be seeing throughout machine learning, right? That it has to be on unseen instances of features. So this is what is called generalization, right? So I mean, I just don't want to memorize my training data, right? But given a new instance which I've not seen before, I need to be able to classify it. So that's the whole purpose of machine learning, that I need to be able to solve for things I've not seen before. That's why it's different from just kind of storing it in memory and just basically memorizing the entire training data, right? All right. So again, classification, we have basically, this is the classification boundary, right? So this is basically the positive classes and this is negative classes, right? So this is binary classification. And then you have regression, right? So regression is basically I'm fitting. So we can call this curve fitting, or I'm fitting a curve to my set of data points, right? So the key aspect in regression is that I have my y, this is a continuous set of data points, and I have my x-axis, right? So, all right, so here we'll actually kind of explicitly see classification versus regression, right? So sorry, there's just a little bit of a lag. Okay, so here we'll see basically explicitly classification versus regression, right? So again, that's the supervised dating scenario. Supervised data scenario. We have a bunch of data points, x1, y1 up to xm, ym, right? These are the training data points. Over here, I'm assuming xm belongs to R, but actually, I mean, we can assume that xm belongs to R raised to D, right? So it's a D-dimensional feature vector. In the regression case, right? So this is critical. In the regression case, ym belongs to R. So actually, it's a continuous value, right? And in the classification case, ym belongs to 0 to k minus 1, right? So this is actually a discrete set of classes, right? So this is basically, all right. So when k is equal to 2, we actually get binary classification, right? So when k is equal to 2, we get binary classification. But in the general case, when k is greater than 2, we get multi-class classification, also called k-class classification, right? All right. So again, just kind of recalling the figure, this is classification. We saw this, we saw regression, right? And the difference between binary classification, here I have two classes, right? These are the positives, these are the negatives, for example, right? Multi-class classification, right? So multi-class classification is where k is greater than 2, right? So over here, this would be, for example, one class that I've highlighted, right? This would be the second class, right? And this would be the region corresponding to the second class, right? And this would be the third class. So this is the decision boundary of the third class, and this would be the region corresponding to the decision boundary, right? So this is what multi-class classification is, and essentially I want to find these regions is the goal, right? So these lines that we are seeing, basically also called the decision boundaries. This is what the model is, right? So the model will try to find this decision boundary. It could be a straight line, or it could be more complicated as a decision boundary, but the model tries to find the decision boundary and tries to segregate between the classes, right? So that's the goal of classification. The case of regression, we are trying to learn this kind of curve associated with the data, right? So it's a curve fitting problem. Okay, so now kind of having set the premise of supervised learning, right, and classification and regression, I'll actually take a look now at a few concrete examples of these. And we have actually seen this before as well, but I'll spend maybe a minute on each of these applications just so that it's clear, right? So classification, the standard example is spam email filtering, right? So spam filters, spam detection, handwritten digit recognition, right? Of course, you could kind of extend this to handwritten letter recognition, handwritten, right? If you write something down on my iPad, for example, right? I want to be able to detect what is written and convert it into a computerized text, right? You could also do this on general images, right? Then there's medical diagnosis, which is actually very important, right? So you have kind of clinical data, certain trials or certain kind of results that patients have got, and then you want to make decisions based on just the way the doctor would do this. You want to be able to do this automatically using AI, right? So how exactly are some of these things done? We'll actually look at this in this course. Fraud detection is super critical for, again, businesses. Banks, for example, need to be able to detect fraudulent credit card transactions, right? How do they do this? They do this using, again, machine learning and AI. Face recognition, right? So all of these are examples of classification. The case of regression, a standard one is housing price prediction. So again, this is super critical. Redfin, Zillow, all of these companies have some kind of a price predictor, right? They predict the price of your home. It's actually a good indicator for if you want to sell or buy a home, based on the kind of scenario, the market scenario, and so on, right? So this is again a machine learning problem. Stock market prediction, right? Kind of a very, very important but yet very, very hard problem, right? So how do you predict the stock market, which is moving all over the place? Weather prediction, market analysis, business trends. So all of these are basically regression problems, and some of these are, as you can see, more complicated than others. Again, I think it's very important, at least my philosophy is to understand machine learning, right? And understand the limitations of machine learning, right? So there are certain problems that machine learning can solve, and there are certain problems which machine learning is still not able to solve, right? And those are extremely, extremely hard problems. I think it's kind of important to understand where we are at with machine learning and where we can possibly go in the future. All right, so we'll go over a few of these few of these examples a little bit more carefully, right? So we will start with the medical diagnosis problem, right? So the medical diagnosis scenario is that I have all of these features, right? So I have blood glucose, I have BMI, I have diastolic BP, and I have age, right? So all of these are features in my feature vector, right? So I have basically a person, right? And I'm converting this person, a human being, into a d-dimensional feature vector, right? So I'm converting this into a d-dimensional feature vector, and the first entry, for example, of this would be blood glucose, right? The second entry would be, for example, BMI. The third entry would be BP, right? Age, and so on. So we have this basically this kind of long feature vector, and we are kind of storing all the parameters associated with this person in this feature vector, right? So now how will machine learning kind of address this, right? So what machine learning will try to do is that it will basically take all of these readings, and then you will get basically different points. Actually, sorry, I'll kind of kind of tend to draw the decision boundary first. So I have all of these data points everywhere, right? And then in you know, in the supervised learning scenario, I actually have my labels associated with this, right? So I have, for example, that this is, say, positive, this is also positive, right? And this is negative, and so on, right? So negative in the sense that these people unfortunately have diabetes, right? And these people don't have diabetes, right? So maybe this is the region of essentially all of the positives, for example, right? So this is the region, I mean, sorry, all the negatives, right? And this is the region, say, of all the positives, right? So all of these are the positive instances. So uh, the goal of machine learning, so the first step, right, in building a machine learning application like this would be actually to get this kind of data, right? So to collect this data, understand what are the kind of critical features, right? So doing the feature engineering. So the first step is basically feature engineering, and second is collecting label data, right? I think collecting data is kind of the most critical aspect in machine learning that people often overlook, right? But this is super important, and oftentimes this kind of makes or breaks the machine learning application of having the right amount of label data associated with the machine learning, right? And then I think finally the third piece over here would be to actually train a ML model. So again, this is something we will actually look at later in the course, right? So this is an application we want to predict diabetes in this case, right? So the label is diabetes. So this is a problem we want to be able to predict diabetes, and we would construct feature vectors in this way, right? So the attributes of a person would be kind of computing the feature vectors, and then we would basically um, collect the label data as to what are the positives and what are the negatives, and then we would actually train a machine learning model on top of this. Okay, so another application is handwritten digit recognition, right? So this is, for example, a data set called MNIST, right? And these are all the instances of, say, the data sets which are, instances which are zero, right? So you can see that these are actually clustered together. So in some sense, this is actually a visualization of the entire data set. So you can notice that all of the zeros are clustered together. Well, it's not surprising, right? Because zeros look similar. However, people write zeros, they tend to look similar, right? Similarly, the threes are clustered together, the fours and the ones and twos and so on, they're all clustered together, right? So the um, idea of this is that I have an image, right? And the image basically, I have an image that essentially has something like a zero, right? So maybe this is kind of the um, I mean, maybe the zero is so. I mean, this is like a handwritten digit, right? So the zero is maybe slightly all over the place, right? And then I basically take this. So the features here are actually, I take the entire set of pixels, right? So I take all the pixels of this. So this will be a matrix, essentially taking each of the pixels in the image, and then I form this matrix, and then I have this ML algorithm that can basically give out the digit, right? So this is a classification problem. I want to be able to predict if this belongs to 0, 1 until 10, right? So this is a 10 class classification. So what we saw over here, whether it's diabetes or not, 0 is basically not diabetes, and 1 is diabetes, right? So sorry, there's a little bit of a lag, but essentially this is, in this case, this is just binary classification because there are just two labels, right? But in the case of the handwritten digit recognition, right, this is a 10 class classification problem. So there are 10 classes over here, right? So another kind of very standard application of of classification is actually spam, right? So spam is I have an email like this, right? So dear blah blah blah, my client is looking for a Java developer. Call me. So some weird phone number. Yours faithfully, right? Or maybe there'll be some like hi. This is something very common, right? Which is there in spam. You have some hi or something like that, and then you have some crazy kind of words, right? Maybe there is the word free over there, right? Things like that. So there are these common words that you know that belong to spam, or there is like a certain kind of an email, right? And you have regular email that talks about regular conversations, right? So there'll be someone's name over there, and then there'll be like, you know, the person who's sending in his name, and then like some kind of a regular conversation, right? So this is spam, and this is basically not spam or ham, right? So spam is another classification problem. We briefly saw this in the first and second parts of this, right? So you take in email, right? And then you take all the words associated with the email, right? So these are all the words. And then you form a feature vector comprising of the words, right? So for example, hi will be one word over here, right? And then there'll be some word like client, right? In this case, and then there'll be another word like free, which probably is a very important word in the case of spam recognition. So you have all of these different words. So right, this model is basically called bag of words model, right? So this is called bag of words model, and the bag of words model basically is that you are kind of representing your entire feature vector in terms of this bag of words. Okay, so the problem here is that given this email, I want to be able to predict whether the label is spam, right? So spam is say a positive one and not spam, right? Which is negative one. Okay, so this is spam classification. So we'll go to the next example. The next example is actually of regression. So the regression one is the house market price prediction, right? So you can see that this quantity over here, which we are trying to predict, right? So I don't know if you can see it very clearly over here, but this is it says over here Redfin estimate, right? And the Redfin estimate is basically $411,000 roughly, right? So how does Redfin come up with this quantity, right? Well, so Redfin has a bunch of features over here. So what are the features, right? So I think one very important feature is actually time on Redfin, right? Another important feature is HOA dues. So HOA dues means that these are the dues of the housing association, right? Then the style of the home, whether it's a single home or a town home, right? Single family, town home. Another very important feature is the lot size, right? So the size of the lot. Then the year built, right? This is probably also a very important feature because it determines in some sense how new or old the home is, and essentially the value determines is obviously determined on that. And there are a few features not listed here, right? So the size of the home. In fact, I think those quantities are there over here. So the size of the home, for example, in this case is 1934 square feet. I think this is a super important feature, right? This is very, very important because typically most homes are determined by the price per square feet, right? So in some sense, the multiplication will depend on this feature, but of course it depends on the other aspects of the house as well. That would be, of course, adding to the final value, right? And then you of course have the number of bedrooms, number of baths, and so on, right? So all of these also add to the price of the home, right? So in some sense, a combination of this kind of machine learning model would take the home price, right? And then it would take the features and then try to fit a function, right? So this is X, this is Y. It would try to fit a function such that I can basically exactly get Y equal to f of X, right? So Y is my label over here, f of X is my features. Okay, so again, I think the house market price prediction problem is actually much more complicated than that because you have a temporal aspect, right? So the price that was there 1 year back I cannot use that data anymore to predict the price today, right? So there is this kind of temporal aspect of the house price increasing, and I have to take all of that into account. It's also something like an online learning problem. It's a continuous learning problem because you have data coming in continuously, right? So you want to be able to update things continuously. But I think the idea is that you need to understand the problem really well, and then understand which machine learning model you can use to actually fit this problem. Okay. We'll quickly go over some others. We have seen this again. An example of a ranking problem is actually search engines, right? So you have all of these. So I just searched actually over here, ranking in machine learning, right? So I got some articles over here, and then I have some more articles below as well, which didn't actually end up coming in over here, right? So the ranking problem is because I want to be able to say that this page is rank 1, this page is rank 2, and so on, right? So again, the features here is that I will take essentially information of each of my instance, right? Features, and the features would be basically web URL, title, right? And then maybe the text within the web page, right? And so on. So I have all of these different details as features. And then my output label is basically a ranked list of pages, right? So I select basically page ID, um, page 1, page 2 until page 10, for example, right? And I want to select which of these pages are ranked 1 to 10. So this is the kind of label, and these are the set of features, and this problem is an instance for ranking problem. Okay. Finally, there is recommendation systems. Again, we kind of saw this very briefly. So recommendation systems is where I want to do movie recommendations. And I have basically my friends' favorites and then watched by my friends, right? So I have kind of friendship information. I know which friends are similar to me, right? So I have my preferences. And okay, so I'll just kind of note down some high level ideas in this thing, right? So I have, sorry. Yeah, so so I have my preferences, and then I have my friends. So basically this is my history, and then similar movies, right? Based on people who are similar to me. So I have my history, I have my friends to give me additional information. So I want to combine all of this to basically create a recommendation, right? A recommendation system. So, all right. So I think with this, I'll actually kind of end the portion of recommendation systems, and uh, we can very quickly go to the supervised learning portion, right? So the supervised learning component is, sorry, we can end the supervised learning and come to the unsupervised learning. So the unsupervised learning is where my data comprises of X1 to XM, as here I only have the set of features, right? So the critical aspect is there is no label, and I want to be able to find the clustering, right? So this is basically cluster 2, this is cluster 1, this is cluster 3, right? So in some sense, I'm given this form of a data that is there over here, right? So given this data, I want to be able to come up with a clustering of this data based on different clusters, right? So this is unsupervised learning. Why is unsupervised learning important? Well, unsupervised learning is important because we oftentimes don't have labeled data, right? So we want to still extract patterns from labeled data. So for example, we want to categorize items in a store or in an online marketplace. We want to categorize items based on similar items, right? We want to cluster we want to cluster customers, right? And we want to cluster customers based on similar buying patterns so that we can have targeted advertisements, for example, right? And we want to do recommendations. So we discuss recommendation systems as a supervised learning problem, right? But you can also view it as an unsupervised learning problem. And then you can basically find similar items that you want to recommend to users. Finally, you want to do things like outlier detection, right? So things like fraudulent activities, for example, these are all outlier detection problems. These are all typically oftentimes unsupervised, though you can view this as a supervised learning scenario as well, right? So unsupervised learning is also a very, very important kind of area in machine learning along with supervised learning, right? So finally, there is reinforcement learning, right? So reinforcement learning is a slightly more advanced topic. I won't go into a lot of detail in this particular course, but I'll be talking about kind of more advanced topics where I'll actually cover reinforcement learning. So the basic idea of reinforcement learning is that I have an agent, right? So the agent is, say, for example, a robot, right? Typically a robot, but it's basically any kind of embodied AI system, right? It could be your virtual assistant as well. And you want to go beyond just making simple decisions that, I want to basically recognize fraud or not, right? Or I want to detect spam emails. So instead of having very specific task specific machine learning models, I want to have a generic agent which can basically kind of uh, help me throughout my life, right? I want to have a robot which can learn like the way we are learning, right? And I want to be able to basically kind of piece all of these different things together. And I think a critical part of this is to be able to make actions, right? So the robot, like we continuously throughout the day, we have different actions, right? And then we do various actions, and then we get feedback. There is a reaction to those actions, right? So the same with AI system as well, that the AI system will try out different actions, it'll explore different actions, right? And then the environment will give it a reward, right? So the reward in some sense is the reaction to this. And the reward can come in various ways. I'm talking about it in a very, very abstract scenario, right? And I think another kind of critical piece in reinforcement learning is that there is a state, right? So the state kind of models my current situation, as to where I am in the, I mean, if you can, the model space, right? And essentially based on my current space and the actions that I take, I get various rewards, and then I can update my policy, right? So the agent essentially inside maintains what is known as a policy that helps it take actions. Okay, so this is again a very, very high, 15,000 meter high view of reinforcement learning. But we can actually kind of, maybe I'll have some special topics that will discuss reinforcement learning in more detail, right? So what's an application of reinforcement learning? Well, I mean, there could be multiple, but one specific application is having an agent like this, right? So each of these are kind of agents. These are all robots, and then they are actually interacting with each other, and the robots can kind of understand that this is the ball, and then they can basically try to take the ball in various scenarios, and if they have a ball, they get a reward, right? And then once they go in the opponent's direction, their reward keeps increasing until they are able to score a goal, right? If they score a goal, then they get a very, very high reward, right? But on the other hand, if they lose a ball, right, so they're taking a ball, but if they miss the ball and the opponent takes the ball, then they get a negative reward, right? So then they learn that these are not actions that they should be doing, right? And if the opponent scores a goal, right, the opponent scores a goal, then again they get a very, very high negative reward, right? So you can basically model the reward structure based on the actions that they take. So the actions, for example, can be to go right, to go left, to go towards the ball, to go against the ball, right? And essentially the ball has a particular coordinate, and the agent will know this coordinate, right? So based on the action it takes, so for example, if it goes in the direction opposite the ball, right, immediately you'll start getting negative rewards, right? This is exactly the kind of premise of reinforcement learning, and it's kind of a very fun yet very evolving, and still I think in a very, very nascent state. Still a lot of progress needs to be made in reinforcement learning, but I think there has been significant progress that has actually been made, particularly in the kind of deep reinforcement learning space. All right. So with this, I'll actually briefly just say that we did speak about this in the last lecture, that there are variants between unsupervised and supervised learning. One of them is semi-supervised learning. There is active learning. There is online learning, right? And very briefly, we actually saw reinforcement learning in the previous slide, right? All right, so with this, I'll actually end part 3 of this, where we actually looked at applications. And then finally in part 4 of this kind of introductory lecture series, I'll actually just define basically the notions of how exactly we would be modeling different problems, what are loss functions, what are evaluation functions, things like that, right? So we'll go over basically more details into the supervised learning framework. So actually, the next several lectures, I think the next 10 lectures will actually be focused on supervised learning, and then we'll talk about unsupervised learning, right? And maybe towards the very end of the class, I will actually have one lecture maybe on active learning, one lecture on semi-supervised learning, one lecture on reinforcement learning, something like that. All right. So thank you guys again for listening to this, and take care. Stay safe.